There's a rule in mathematics that seems so harmless, so obviously right, that most people accept it without a second thought. But once you do, reality starts to twist. You find yourself staring at a ball that can be split into pieces and somehow reassembled into two identical copies of itself. No tricks, no extra material, just math. This idea has haunted mathematicians for over a century. It's elegant, powerful, and deeply unsettling. And it all begins with one simple question. How do you choose something when there's no way to choose? Try this. Pick a number. You might say 12 or 81, or maybe pi if you're feeling fancy. That's your brain doing the work, filtering, evaluating, selecting. But math isn't human. Math doesn't guess. It doesn't feel. It needs structure, a rule. Because in the world of math, randomness is just an illusion. Even computers, which we call random number generators, aren't truly random. They use formulas, timestamps, patterns, all deterministic. So what happens when math needs to pick something from a set, but there's no natural rule to follow? We run into this problem with real numbers. Unlike whole numbers or primes, which have obvious starting points, real numbers are a messy soup of decimals, irrationals, fractions, with no clear first or next. Try choosing the smallest real number greater than 1. You can't. There's always another one, just a little closer to 1.1, 1.01, 1.000001, 1.00000001. It never ends. There's no foothold, no place to begin. And yet somehow, we want to believe we can make choices anyway. This puzzle drove one man nearly to madness. In the late 1800s, a German mathematician named Georg Cantor decided to map out the infinite landscape to see whether you could bring order to chaos. At the time, most people believed infinity was just one thing: big, endless, undefined. But Cantor wanted to go further. What if some infinities were bigger than others? He started by comparing two sets: the natural numbers, 1, 2, 3, 4, and so on, and the real numbers between 0 and 1. Now, there are clearly infinite natural numbers, and there are infinitely many real numbers between 0 and 1. But are those infinities the same? Cantor thought, let's try to list them all. Every real number matched with a natural number. Seems possible, right? But then came his famous move, the diagonal argument. He took that list and built a brand new number by changing the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on. The result? A real number that wasn't on the list. No matter how you tried, there would always be a number left out. Meaning the real numbers can't be paired up one-to-one with the naturals. Infinity, Cantor showed, comes in sizes. Countable infinities, like the naturals, integers, and even fractions, can be listed in a sequence. Uncountable infinities, like the real numbers, cannot. It was revolutionary and horrifying to many. Cantor's ideas were called pathological. One critic said they were a disease eating away at mathematics. But Cantor wasn't finished. He believed that even these uncountable infinities could be arranged, step by step, in a specific order. He called it a well-ordering. For a set to be well-ordered, it needs two things: a clear first element and a way to find a first element in every subset. The natural numbers fit this perfectly. Start at 1, then 2, 3, and so on. The integers, which stretch in both directions, can still be well-ordered. 0 comes first, then 1, -1, 2, -2, and so on. But the real numbers? Nobody could find a starting point. No rule, no pattern, no formula. Yet Cantor insisted that such an ordering must exist, not because he found it, but because he believed it had to. He believed so deeply, in fact, that he once claimed God had revealed the truth to him. This conviction became the seed of the Axiom of Choice, a principle stating that given any collection of non-empty sets, you can always choose one element from each. It seems innocent, even necessary, but with it, we get paradoxes, like the Banach-Tarski paradox, where a solid sphere can be split and reconstructed into two. or sets with infinite points that somehow have no length. All of this just to say, you can pick one. Cantor paid a price for his vision, ridiculed, rejected. He suffered breakdowns and spent time in mental institutions, but today his work is the foundation of set theory. Modern math wouldn't exist without him, and the axiom of choice, still controversial, still debated, but accepted by most, because without it, so much of mathematics falls apart. So next time you pick a number, remember the man who tried to bring order to infinity and nearly lost himself in the process.